right, so let's go to turn your book to chapter 10.
No.
Are we skipping 9.7?
Yes.
With your permission.
Okay.
Okay?
You have permission
Yep.
to not do anything.
All right. We're going to skip 9.7 and go on into chapter 10.
10.1. Does that mean we have another task?
That means that we've got another test coming up. Yeah. So next week I'll hand out the chapter 9 test.
A little bit.
A little bit. 1 week.
Is next week the last class we have before spring break? I think it is. Yes. Right?
Spring break.
So you'll have extended time to take your test over spring break. Because I'm just going to give you the normal amount of work. I still can't. I'm still shocked that some teachers like give extra work when you've got a break. I'm like, really? Give them a week off, right? Come on. These guys work hard.
I agree.
Right? This is a lot of work.
I agree.
So, you
And we
need a
have
break.
other classes.
Sometimes
I
you just need a
know.
break.
It's like,
So,
why not have a why have a day
let's
off
talk about
if
section 10.1, tangents to circles. All right, so let's define some things with circles just to make sure that we remember all of this. And we've got a point in the middle that we refer to as a center, right? I can draw a line all the way through that center point. We would refer to that as a diameter. And when we draw a line just from the center to this edge, we call that a radius, right? So those are parts of the circle that you should already be familiar with. But there are some other things that I want to make sure that we know about. And so if I draw another circle here, and we draw a line that goes like this, it just touches right on the edge of the circle there. And we're going to label that line K. And then we're going to draw another line that goes all the way through here. It intersects the circle in 2 places. And we're going to label that line little j. And then we're going to draw a line here. That just, not a line, but a line segment that's inside the circle and runs from point P on the circle to point R on the circle. And we're going to define each of these things. We call this line segment PR, we refer to that as a chord. So just want to make sure that when we use these terms, you know what I mean. So it should make sense, based on that definition, that the diameter then is a chord that runs through the center, right? So the diameter is a chord. Little j, line little j is referred to as a secant. I was going to ask if anybody knew, but all you guys have your books open, so somebody would inevitably look at the book and just read it out of the book, and that's not what I was asking. And then K, if it's a line that just hits that one point there, then we would say that's supposed to be a little k. I was like, why did I use a big K for that line? I was trying to do little letters for the lines versus the line segment. K is what we call a tangent. So if it just skims the very edge of the circle and intersects it at one point, we refer to that as a tangent.
Is this the same tangent that we were talking about in the trig functions? Like
So I should know the answer to that question
like why are they?
because I feel certain that they are related, and I'm teaching pre-calculus, and we have not. I don't think we've used the trig functions, but I don't think we've done anything where we've explained why those terms are the same. But I just feel like there's probably in one of the calculus classes that I took that we talked about why they use the same term, and I don't remember what that is off the top of my head. So I believe they're related, but I can't tell you for sure for why that is. All right, I could tell you why it is, but your mind would explode. You just wouldn't be able to
I can
contain
tell
the
you, but I
knowledge.
have to tell you.
Yeah, I just don't remember, so I'm sorry. That's a good question. I feel, yeah, they're just it's too weird of a word for them not to be related, right?
Yeah, exactly.
They gotta be
That's what I was
related
thinking.
somehow.
I can't see why they would be related because,
Yeah,
I mean, obviously I'm just learning
yeah.
geometry.
I don't know why that would be, and it's definitely beyond the scope of this. Well, at least beyond the material that we're going to cover. If they are related, why they would be. So let's You got me thinking about that.
Mr. Walker.
Yes. Yeah, you know what?
I think theorem 10.1 will explain it.
10.1 is going to explain it?
I think so.
Really?
10.2.
No way. So how it's related to the trig function?
I'm not sure about directly the trig.
Well, that's what I'm talking about. I'm just trying to, because that was the question, and I'm like, I don't know. I don't remember. I feel like I should know that they are connected and how they're connected, but
Like why would they have the same name?
yeah, right. Like I'm looking at one of the pictures in here, and it has a line. It shows like the tangent. Tangent lines are so hard to draw without like either not touching the circle or just totally missing it. You know. So like if I were to draw a diameter here with this, and I drew a line. So they show like an example of where you draw a line that's like where that's a right angle, where you draw a line to the center point from the tangent and form a right angle. And if I'm thinking about that, this is then that's like, you know, if I were to draw that, this is a right triangle, and so we've got like these two angles here, and tangent is related to, if I'm looking at this angle, tangent is related to these two sides, right? For both of these angles, takes those sides. So does it have something to do with that? I don't know. I just don't remember. But I'm thinking it's something along those lines, right? That's why they're related in name. So let me chew on that. Maybe I'll have an answer for you next week.
Research.
That's right. Thanks. It's like I didn't have enough to do this week. Appreciate you asking that. No, that's a good question. That is a good question. All right, so let's talk about intersection. Just make sure that we understand that. So if we have two circles like this, it should be clear to us that we have 2 points of intersection. Right? We're just kind of defining some things at this point, so we can talk about all of this stuff. So we've got 2 points of intersection there. We could have what you call tangent circles.
Isn't they?
What's that?
Isn't they?
Oh, thanks. And if we draw that, here's our outer circle. And so we've got this inner circle. It looks like that. So we've got two circles, one inside the other, and notice they intersect right here at this one single point. Right? So only 1 point of intersection. And we call these circles here are internally tangent. All right, so that's one set of tangent circles. And then we can have another set of tangent circles that were externally tangent, where again they intersected at just one point, right here. One point of intersection again. But the circle's on the outside this time, so this is externally tangent. And then kind of at least for this portion, we could have circles that look like this, where we've got a circle here, we've got another circle here, and really need to. This is where it'd be nice to be on a computer and I could just take this whole circle and slide it slightly this way. So it's supposed to have the same center point. So let's see if I can, that's terrible. I knew that was gonna happen. Let's try that one more time. So here we go. See, this is what my trig teacher taught me. So here's my point. And I want to do this. That was awful. It didn't work at all like what he said. There's my center point. This is not going to work. All right, let me go around this. I'm just going to eyeball, try to keep the same distance from the circle. There we go. All right, so they have the same, that's not bad. They have the same center point, same center. Those are called concentric circles. I'd love to see that guy again and say, hey, I've never forgotten what you said, but it doesn't work. I never can make it work. Drawing good circles.
I remembered it, but it's not exactly working.
It's like the only thing I can remember that he ever said. You might not be happy about that part.
He's not the best teacher.
He was a great teacher, actually.
That's the only thing he
That's just the only thing that stuck with me. I mean, I'm sure much has stuck with me, which is why I did so well in math after that, right? I just can't remember him actually explaining that. That's the only thing I can remember him explaining. So let's just do a couple of examples. Just go through a couple of examples to make sure that we're tracking so far. You know, I'm going to go ahead and give you one more. More definition here. And then make some room for that. So I'm going to erase this. And I'm going to erase this because I think that was pretty obvious. Right? That was one with 2 points of intersection. It also should be sort of obvious that if I draw these two circles here, they have 0 points of intersection. I know, mind blowing, but I think you guys can handle it. I got a smart class here. So a line segment that is tangent oh, I knew I did something wrong. I did that somewhere else. I'm like, that doesn't look right. Where else did I write tangent like that? Right here. Is that the only place? Yeah. So a line or segment, sorry, that is tangent to TO space TWO, coplanar circles. What do I mean by that?
Circles that are on the same plane.
That's right. So am I the only person that when I hear something like that, I'd like to see an airliner cruising along, a couple of circles sitting side by side, hanging out and just kind of chat pretzels and Coke, you know what?
Yeah.
Coplanar, yeah. It's just me. That's just the way my weird brain works, right? So they're on the same plane. So any of these two circles that I've written on this board are coplanar, right? All of these circles are coplanar because the board functions as the plane that both of those are on, right? We have two circles on a coordinate plane, then they're coplanar. So a line or segment that is tangent to two coplanar circles is called a common tangent. All right? So what do I mean by that? For example, if I have two circles that look like this, one looks like this, and another circle looks like this, and I've got, oh man, this is gonna be tough. Like that, and I've got another one that looks like that. I think quite good. They're supposed to be tangent to both, right? So these are, these lines are both common tangents, and we refer to this as common internal tangents. I did it again. Tangents. Common internal tangents as opposed to this, the similar, something that looks like this. And then line kind of a little wavy there. There we go. All right, so these are common external tangents. Okay? And how do we tell the difference? Well, if I draw a line segment that goes to the center point, that runs between the center point of both circles, and it crosses the tangent that's common to each, then it's an internal tangent, okay? But if I draw a line between the centers, or a segment between the centers, and it doesn't cross the tangent, then it's an external tangent. Does that make sense? So these are common external tangents, these are common internal tangents. All right, any questions about anything that I've written on the board up to this point? Like I said, all just sort of definition stuff, just getting this out here and making sure that these terms make sense, so that you'll understand the language when we begin to introduce theorems and work some problems. No questions? You guys are all still awake? Barely.
Somewhat awake.
Did we end at 2?
Yes.
So,
Wow.
and no one's outside the door yet. That's
Yeah, that is weird. All right, so obviously we're not going to get as far as I wanted to get today. Can you believe I wanted to get through 3 sections?
What?
Wow.
Crazy, right?
Oh,
Crazy.
where's the, overachieving.
It's not going to happen. I'm just going to assign them and let you guys read the rest. How does that sound?
Sure. I'm down for that. I am down for that.
All right, so let's just see if we can get through this section, okay? Let me introduce a couple of theorems. And this is
right.
theorem 10.1. Theorem 10.1 says if I have, so basically this is my drawing to go with this. I've got a line that is a tangent to this circle. It intersects at point P and runs to the center, which is point Q. And our line is L. And so what this theorem says is that if a line is tangent to a circle, All right, and I'm gonna, here's how I'm gonna write a circle from this point on. I'm gonna just write a little circle with a dot in the middle. Okay, so that's gonna be my symbol for a circle. So I wanted to write a circle with it. You guys cool with that?
Oh, because if you didn't think you got it,
You're thinking, oh, that's right. All right, so do the little dot to show there's a center point there. So if a line is tangent to a circle, then it is, what does this mean? Perpendicular, right? It's perpendicular to the radius drawn to a point of tangency. That's just a fancy way to say the point where the tangent crosses, goes through, right, on the circle. So in other words, the simplified, if I had the drawing, the simplified way to write this is that L has got to be perpendicular to QP in my drawing here. That's theorem 10.1. This theorem, we're going to give you 10.2 because it's kind of like the converse of, or the inverse, or however you want to say it, converse of 10.1. If line L is perpendicular to line segment QP at P, then L is tangent to circle Q. I really should have made the center point Q, because I mean K, then we could have said it's tangent to circle K. See, Joshua?
So earlier when you wrote the right angle on the example earlier, we were talking about the relationship between two tangents. Is there in 10.1 like how you needed to put the angle there?
Yes, exactly, because it says it's perpendicular. Yeah, so that's why I knew that was a right angle, and so it's like, well, you can kind of see where tangent relates to this if you've got right angles inside your, related to your tangent line. But yeah, good question. All right, so that was Joshua. Cameron said something a minute ago that I was like, I need to write down her name. All right, there's one more theorem. Let's just go ahead and.
Mr. Walker, shouldn't that be theorem 10.2? Got to 10.1.
Oh yeah.
10.1.
Good catch, good catch. That would have been confusing.
That would have been.
I was saying the converse of 10.1. I wrote down 10.1. All right, and so what's our last theorem for this section? The last theorem, theorem 10.3.
Yeah.
And that one says, if you have line SR and line ST, and those are tangent, if they are tangent to, we're gonna do it this time, circle K.
Yeah.
All right, tangent to circle K. Hey, it looks like okay. With a dot in the middle. Then SR, line segment SR, is congruent to line segment ST. All right, so this is what our drawing of that looks like. We've got a circle here, with a center point K,
Okay.
and we've got this line that's tangent here, and we've got this line that's tangent here, and we've got a point S here, and we've got a point R here, and a point T at the bottom where the tangent is, and then we've got a point S. Right, this line segment is congruent to that line segment. Clearly, I did not draw this to scale, but that's what, you will do a much better job. That's what that theorem says.
Whenever we have a quiz or test, can there always be at least one circle K?
Circle K, okay,
Yes,
yeah.
always.
I gotta do that, right, from now on.
So,
You won't accept anything else.
All right, so
yes.
Just a little long strike.
let's just do a couple of problems real quick, right? So we can use all of this knowledge that I've just dumped into your brain. The example 4 says use the converse of the Pythagorean theorem to tell whether line EF is tangent to circle D. Okay, and so they give us this drawing where we've got a D in the center here, and we've got this out here, and we've got a tangent that's running right there, and we've got a line here. They tell us the length of this is 11, and they tell us that this is 61, and they tell us that this is 60, and they tell us that this point is F. And we're trying to see, is EF in fact tangent to this circle? What do we need to prove that it's tangent to the circle? If it's tangent to the circle, we're going to have a right angle where?
Point E.
What?
Point E.
Point E. That's right. All right, so if that, since you raised your hand, Aiden, if that's a right triangle, then we've proven that it's tangent. And so what would I do to determine if that was a right triangle?
With the Pythagorean theorem.
Use the Pythagorean, so what numbers would I use?
You'd use 61 squared equals 60 squared plus 11 squared.
That's right. He did c squared equals a squared plus b squared, right? So this has got to be true if in fact that this line here is tangent. If line segment FE is tangent to circle D, right? So if we punch that in our calculator, maybe it is, I'm kind of doubtful, but does that turn out to be, are they equal?
Yes, sir.
They are? Wow. I wouldn't have guessed that, but not like I know the square of 61, so. So yeah, the square of 61, they don't actually list it, but this turns out to be a true statement, so we can say that it is, in fact, tangent. Line EF, a line that runs through those 2 points is tangent to circle D.
Still nobody outside the door.
So for this, look at this. This is kind of a cool one. If we have a circle, I mean, there's things that you can figure out from this, right? That you wouldn't even really, that wouldn't cross your mind until you start learning about this. But if you've got something that looks like this, and you've got a length R here and a length R here. This is 16 feet, and this is 8 feet, and we're told that we're standing 8 feet from a grain silo, right? So this is us out here at point C. This is B, and this is A. And the distance from you to a point of tangency on the tank is 16 feet. So I'm standing here 8 feet away from the closest edge, but if I draw a line to a point of tangency, then that's a distance of 16 feet. What is the radius of the silo? And so how would we figure that out? Well, because I know this is to a point of tangency, then I know this angle is a right angle, right? Everybody agree with that?
Mm-hmm.
So do I have enough information to figure out R at this point? You guys knew I was going to ask that question. That's why you're
So that would
smiling,
be-
right? It's like, duh, of course.
Should be 16 squared plus r squared equals r squared plus 8 squared.
Well, what's our hypotenuse in this right triangle?
16 feet.
No,
That
it's
is not
r
true.
and then 8 feet.
plus 8 squared.
R plus 8. Or did you, well, I just want to
And
know what the
then all that
hypotenuse is. The
squared.
hypotenuse is R plus 8. Does everybody see that?
Yeah.
All right, the hypotenuse is R plus 8. So we could say, so this would be like our C in the Pythagorean theorem. So we could say A is, we can make A equal to 16, and we can make B equal to R, right?
Yeah, so that would be
So
r
A squared plus B squared equals C squared means that 16 squared plus R squared has to be equal to R plus 8 squared,
Okay,
right?
that's what I thought.
Yes?
18?
Huh?
18?
18?
For the complete angle.
the complete line, this right here?
Yeah,
So you're telling me that it's 18?
yeah.
And you just did all that math in your head and came up with that? Wow. Is that right? That's not right. So I couldn't do that in my head. That's why I was about to be really impressed. But
Close.
because I don't know what it is close. Yes. So how would we solve that? What's 16 squared?
256.
256. All right. 256 plus r squared equals, and we have
R
to use
squared.
the FOIL method here.
Uh,
Do you guys agree?
Yeah, R
Is there an easier way to do that?
The FOIL method.
R squared plus 864.
R squared plus 16r
Uh,
plus 64, right?
Oh,
wait,
So that's all of it. You guys agree with that?
yeah.
Did I do that right? 8r plus 8r is 16r, and then 64 is 8 times 8. All right? So let's move all of our numbers to one side and all of our r's to the other side. We'll put our r's over here on the right. So we got r squared minus 16r equals 64 minus 256. Okay? These r's cancel out, so we've got negative 16r equals, huh?
Wouldn't it be easier to shift the r's to the other side?
Doesn't matter.
Well, I mean,
It's you talking with the negative sign?
they wouldn't have to work with negative numbers.
Yeah, it doesn't matter at this point. I've already done it. So,
Okay.
all right. I want you guys to be good. I moved it over there. I was like, I could have left it positive, but I moved it to this side so we'd have the R on this side. So you guys should be able to handle that either way, right?
Okay.
64 minus 256 is what?
192.
192. Negative 192,
Okay.
right? And so we divide both sides by negative 16.
That is 12.
R equals 12. All right. So, David and Dave, I appreciate your participation.
Thank
right? Even if I shot down your ideas. And then Camille, you were in on that one as well. Does everybody understand how to do it? Any questions about that? Wait, what are you doing? You've got like 30 seconds left. Are there any other questions?
Are we gonna have a quiz over one section next
We're
week?
gonna have a quiz over one section. Yeah, I think this is probably enough stuff that I want to test it and make sure you're getting it. Okay? We'll plan to have a quiz over this one section next week. All right?
Alright.
All right. Now you may leave. Got your money's worth. All right? Have a good day.
The 30 seconds makes the difference though.
That's
Yeah.
right.
Every second counts.